At 9:47 on June 6, 1944, over a strip of chalky earth in northern France, a single P-51 Mustang touched down with an economy of motion that belied the chaos around it. The landing came after a thin trail of oil smoke had threaded the blue, the propeller biting the air in a tired cadence, and the pilot had guided the machine away from flak and into a field that would become the site of an unplanned technical inquiry. The sound of the motor Merlin had faded into an anxious hush, the smell of hot oil and scorched fabric hanging in the cool morning air. What began as a mission to escort bombers became, within hours, the most valuable wreckage any intelligence unit in the area had ever found. In short order, the aircraft disappeared behind canvas tarps and into trucks bound for a testing facility whose very name was spoken in thin, confidential tones. The opening scene held a paradox of sensation and calculation. The Mustang looked like a tool of mass production, cleaned by war and still gleaming in its rivets, but its internals whispered secrets of design that were not yet understood by the unit that recovered it. The immediate image was tactile motor vibration turned to silence, the metallic tang of spilled fuel under canvas, the whisper of pages being turned in hurried logbooks. The surprise that would drive the investigation was simple and profound. What if this plane was not merely another Allied fighter, but a design that shifted performance envelopes in ways that required a doctrinal rethink? The promise of revelation pulled officers, engineers, and pilots into a single puzzle. This film reconstructs that puzzle from flight logs recovered at the scene, official test center reports, interrogation transcripts, and the diary of one man who climbed into the Mustang and reported back in language that stunned his superiors. The protagonist who carried the technical weight of the story was Oberleutnant Hans Lurch, a 32-year-old German test pilot with formal engineering training and a reputation for methodical risk-taking. He would be the man whose notes and testimony converted curiosity into quantified assessment. Opposite him in the human ledger was First Lieutenant Thomas Frazier, the American Mustang pilot whose forced landing started the chain of events and whose initial log entries provided a baseline of performance and damage. Both men would be central to what followed, and both would leave accounts recorded in reports that would feed strategy and doctrine. Among the documentary sources used here are the Reckland Central Test Center Evaluation Report number 47, the flight logs of Thomas Frazier, the diary entries of Hans Lurch, and intelligence summaries maintained by Captain Eric Vogel, all of which we will cite and draw on to reconstruct not only the mechanics of a machine, but the tactical consequences that followed. Recovery crews arrived with a sense of urgency that was more bureaucratic than theatrical. Under the direction of Unteroffizier Carl Schmidt, and with Captain Eric Vogel overseeing security, the Mustang was surveyed on-site, photographed down to the smallest plate number, and tagged with a chain of custody that began the process of turning a wartime find into an evidence trail. The team smelled diesel and the earth where landing skids had torn up clods of clay. They felt the stiffness of seized control cables and probed the skin of the fuselage for microdents that would tell of stress distributions. Lieutenant Friedrich Baumann, the on-scene mechanic, called out serial numbers while Sergeant Josef Meyer and Corporal Hans Richter prepared crates and lifting slings. The transportation plan called for the aircraft to be moved under tarp to a mobile decontamination station, then onto a low loader bound for the Reckland Center, a 4-hour trip that would be conducted under radio silence and blackout conditions. Time was a pressure valve. Every hour the plane spent unprotected increased the risk of sabotage, tampering, or improvisation by locals. The recovery was methodical but hurried, the men moving with practiced efficiency and a sense that this machine could alter more than the career trajectory of any single mechanic. At the Reckland Center, the scene changed from field recovery to institutional scrutiny. The hangar where the Mustang arrived smelled of oil and hot metal, a space lit by swinging lamps and muffled conversations. There, the chief engineer, Dr. Marta Weiss, coordinated an intake team while Professor Otto Brandt, the resident aerodynamicist, prepared baseline measurement tools. The facility had cobbled instrumentation, a set of portable dynamometers, a series of hand-drawn calibrations, and a rack of spare gauges scrutinized by Gerhard Kine, the instrumentation tech. The center functioned as a cross between a laboratory and a courtroom, with evidence presented and countered by specialists. The layout was efficient: benches for stripped down, benches for instrumentation, and a raised catwalk where observers in coats watched as panels were removed and as the inner heart of the Mustang was exposed. The backdrop was international tension. Resource allocation committees awaited verdicts. The Armament Bureau wanted confirmation of what the capture meant, and training commands already speculated on changes to instruction of pilots. The test pilot designated to fly the captured machine was Hans Lurch. His file recorded flights in 30 different airframes, classes of high-speed dives and low-speed stalls, a long record of steady analytical notes, and a near-obsessive attention to instrumentation. His reputation in the testing community was of someone who treated a cockpit as a laboratory. Hands measured inputs, instruments were treated like subjects, and each maneuver was a data point. Lurch had been selected not only for his skill as pilot, but for his engineering sensibility. He read blueprints more fluently than most commanders read orders, and he spoke of center of pressure coefficients and cooling graphs the way other men spoke of weather. His relationship to the Mustang would not be one of conquest, but of method. His goal to produce reproducible numbers that could be translated into doctrine. The presence of Lurch had tactical implications because a test pilot with his credibility could convert anecdote to policy. Before the first flight, there was a detailed inspection and debate about what to repair, what to leave in its captured state, and how much to emulate operational conditions. The inspection was exact and surgical. Panels were removed, inspections logged, components photographed, and wiring traces followed. Mechanic Carl Schmidt argued for replacing only the most critical items to maintain a degree of realism, while Dr. Weiss insisted that certain fragile instruments be protected to allow meaningful data collection. The discussion was technical and emotional at once. The men touched the fabric of the Mustang, felt the weight of each rivet, and argued about the ethics of altering an enemy machine for testing. They checked the radiator and cooling circuits, the fuel lines, and the oil system, reading values on portable manometers and thermocouples. Small decisions mattered. A bad plug or an uncalibrated gauge could make a test invalid. The procedural heart of this operation was a balance between operating the machine as a captured piece and protecting the integrity of data. The pre-flight dialogue was extended and revealing. In the hangar, Lurch conferred with Dr. Weiss and Carl Schmidt. Lurch said, "You will leave the supercharger settings as found. We need baseline data, not a polished museum piece." Dr. Weiss replied, "Our instruments will be shielded, but we cannot fly with known leaks." Lurch answered, "Then we patch the leaks in ways that mimic field repairs." Schmidt interjected, "If you ask me, we should replace the spark plugs." Lurch said, "Not if we want to see what the original unit gives us." Dr. Weiss asked, "How do you handle unknown quirks in the cockpit?" Lurch replied, "Slowly and iteratively." "Will you check the radios?" Schmidt said. "They could be rigged." Lurch said, "I will not use radios on the first sortie. I want raw handling." Words were measured, hands were steady, and the final decision was to fly with minimal alteration while recording as many parameters as possible. That dialogue contained not only technical decisions, but an ethics of testing that would govern how the data was interpreted and applied. The preparation included a technical procedure described here in concise terms for clarity. Technicians performed a bench test of the motor, Merlin, with a portable load bank, recording oil pressure, torque, and RPM across a 5-point sweep. Fuel flow rates were measured at nominal power settings, and cooling throughput across the radiator was verified by dye tracing. Control surface rigging was checked within 1 degree tolerance, and instrument calibrations were cross-referenced to the Rechlin master gauge. A standard form was completed documenting serial numbers, torque readings, and any deviations from the capture state. This process ensured that the first flight would yield data comparable to the center's archived baselines. The first flight became a crucible of sensory detail and technical process. Observation. Engine vibration was felt through the seat. The scent of warm oil entered the cockpit. The canopy steamed slightly during rapid climb, and a faint electrical smell suggested marginal insulation. Lurch reported in clip notes that the throttle response was clean, the roll rate was quicker than expected, and that the Mustang maintained altitude with a lower power setting than comparable machines. He described the feel of the controls as precise, almost surgical. During flight, instruments recorded acceleration curves, wing loading, stress markers, and temperatures, which later translated into comparative coefficients of drag and lift. The readings indicated that at altitude, the Mustang sustained higher speeds with a lower fuel penalty than contemporary designs, raising immediate questions about the implications for escort range and combat endurance. The effect in the hangar when telemetry returned was audible. Whispers became clipped statements, and those who had expected incremental improvement found themselves facing a potential leap. A clear moment of tension unfolded when Lurch performed a high-speed dive to test compressibility effects. The cockpit rattled and the horizon bucked. The control stick felt heavier. An unexpected vibration began at what should have been a safe regime. He pushed forward, trimmed back, and then felt the wing's feedback lessen as shock began to form near the leading edge. The decision to recover had to be made within seconds. Lurch recounted his thought. "Not yet. Not now. I will bleed off speed with slight back pressure." He eased the control while calculating angles and servo loads, and the Mustang responded not with violent buffet, but with a stubborn loss of lift that felt like a velvet hand pulling him down. He arrested the dive and climbed out, monitoring oil temperature and control pressures. The result was a close call, one that produced data on a threshold few had explored, and would later be used to refine training on high-speed approaches. A second tension came when maintenance discovered that the radiator cowlings had been reinforced in a way that suggested field improvisations. The men in the hangar argued if these reinforcements had been standard issue or ad hoc fixes carried out by crews in the field. Captain Eric Vogel demanded answers, while Gerhard Klein sketched diagrams and Dr. Weiss ran comparative stress tests. The question mattered because it bore on durability and repairability. What could be fixed in the field and what required factory intervention? If robustness came at the cost of maintainability, that had operational consequences. The debate turned on measured tolerances and the plausible downtime of replacement parts, which would change how maintenance units were prepared. A third tension was human. News of the capture reached a command level that saw political as well as military value. Some officers wanted to publicize the capture as propaganda. Others argued for utmost secrecy. Lurch found himself in the middle, summoned to brief a room of senior officers, discussed in clipped military terms. "They want a headline," Lurch replied. "I give them numbers." The room had a collective awareness that numbers could alter production priorities and that a premature leak could trigger factories to change direction. Lurch's passion for precision created friction with those whose currency was headlines. Backstories framed the motivations and temperaments of our main protagonists in human scale. Thomas Fraser had been raised in a Midwestern town where thunderheads rolled over wheat fields and where mechanics were respected as men who kept the world running. His childhood hands learned to change oil and tune engines before they learned to read maps. He enlisted as soon as he could, and his flight training became a continuation of hands-on curiosity. He logged hours in trainers, then in early fighters, learning to listen to motors and to speak the language of gauges. The wartime acceleration of training denied some rites of passage, yet granted a young pilot a swift path to responsibility. Fraser's logbooks showed care and habit notes about engine temperaments, a tendency to annotate the smell of fuel or the pitch of a propeller's note. These small attentions would become evidence when his landing produced a machine that others wanted to analyze. Fraser's turning point came in a mission where he had to choose between escorting a bomber formation and diverting to intercept a single enemy fighter that threatened a convoy. He chose the bomber and watched as the convoy later reported being attacked. The memory of that choice cost him nights of sleep and matured a pilot who negotiated risk through protocol and a measured conservatism. When forced to land, he chose fields that preserved the aircraft even at the cost of capture, because he believed in leaving the machine intact for repair. That decision would ripple outward and put an intact example into hands that would test and measure it. Hans Lurch had a different arc. Born in a port city where ships came with stories and engines were instruments of national pride, he pursued engineering with the zeal of someone who liked certainty in a messy world. He excelled in fluid dynamics and grew fascinated by how small changes in curvature or cooling could produce nonlinear gains. His training as a pilot came later as a practical complement to engineering study. He wanted to see the devices he designed respond under load. A career turning point occurred when he survived a structural failure incident early in his test career by virtue of calm analysis and quick corrective inputs. That event hardened his methodical approach and created an ethos of measured testing rather than bravado. As a result, his reports were prized for their clarity and immediate applicability. Lurch's present life at Rechlin was one where calculations and cockpit instincts coexisted. He kept a diary in which he wrote not only numbers but impressions, the way a scientist might note a curious animal's behavior. His first encounter with the Mustang began with a tactile assessment, the grime under a cover, the way a weld had been dressed, a small solder blob on an instrument bezel. He saw in the craft not a trophy, but a complex system whose faults and virtues could be isolated and translated into production directives. That stance would make his revelation more credible in the eyes of engineers and less palatable to propaganda officers who preferred simple categorical judgments. The analysis and the resulting report were methodical and technical. Lurch and Dr. Weiss produced a formal evaluation that recorded thrust output at altitude, climb rates, and sustained cruise efficiency. They compared the Mustang's performance in 3 regimes: low altitude, medium altitude, and high altitude, and measured fuel consumption at equivalent power settings. The instrument data suggested a lower coefficient of drag in cruise than expected, with a corresponding improvement in range of roughly 10 to 12% under comparable load factors. The cooling system design allowed operation at higher sustained power settings due to an efficient radiator layout that reduced hotspots. Control harmonization provided faster roll rates without a proportional increase in stick forces, indicating optimized linkages. The report concluded that the Mustang combined a high service ceiling with endurance attributes that made it effective as both an escort and as an interceptor in certain tactical envelopes. These conclusions were backed by tables of RPM, torque, fuel flow, and temperature traces, and by annotated flight logs. The strategic implications were immediate and broad. A fighter that could escort heavy bombers farther from base while maintaining fuel reserves changed the calculus of escort doctrine. Commanders who had previously assigned layered escort squadrons faced the prospect of extended single sortie coverage, altering the disposition of resources and the scheduling of maintenance. Training programs needed to emphasize endurance management, and pilots required instruction on exploiting the Mustang's cruise advantages without exceeding compressibility thresholds. Production lines took note of component tolerances that mattered most in field repairs, and logistic planners revised spare parts packages to reflect the radiator design and top-end cooling characteristics. The tactical chain reaction extended to unit performance, where squadrons equipped with Mustangs could operate with fewer rendezvous points and less vulnerability to fighter interruptions over hostile territory. A fourth moment of acute tension concerned morale and secrecy. Word leaks were inevitable in a theater filled with rumor and grief. Some local papers hinted at a captured American plane, prompting questions from political handlers. Captain Eric Vogel convened a meeting where he insisted on strict confidentiality, while others pointed out the morale value of announcing a capture. The choice was a strategic communication decision as much as a military one. Lurch found himself writing an internal summary for high command that balanced the need for secrecy with the practicalities of interdepartmental resource allocation. The tension resolved into a policy that classified technical findings while allowing limited internal dissemination to procurement bureaus. Throughout the narrative, a cast of secondary players appeared by name and action. Unteroffizier Carl Schmidt oversaw salvage and made pragmatic repairs. Sergeant
Josef Meyer handled transport and logistics, securing slings and crates. Lieutenant Friedrich Ballman recorded serial numbers and negotiated with local civilians. Corporal Hans Richter assisted in strip-down and in sensory inspections. Dr. Marta Weiss coordinated instrumentation and ensured calibration. Professor Otto Brandt provided aerodynamic interpretation and translated flight data into coefficients. Gerhard Klein managed gauges and performed bench tests. Captain Eric Vogel managed security and coordinated with intelligence. Each of these men and women contributed a discrete action recorded in logs and in testimony that would be used to corroborate Lurch's conclusions. The CTA moment arrived after the first full test sortie when viewers have absorbed the technical surprise and the human stakes. If you were surprised by the performance details we have just shared, you are not alone. This capture shifted question marks into numbers, and for those of you who follow military technology, this kind of discovery is rare. In the comments, tell us what you would do if you found an intact enemy aircraft in a field. Would you study it, fly it, or hide it? Start your comment with "I would" and then give your reason. For example, I would study it because I want to understand how components fail or hold up. Your answers help shape future episodes. We often pick viewer scenarios to test as mini investigations, and we read each comment to refine the kinds of technical reconstructions we make. So write your line and tell us whether you would risk flying a captured machine or keep it under lock and key. Your perspective matters, and it feeds the next story we tell. Now back to the hangar and to decisions that would affect doctrine. The formal report that followed included a series of recommendations that would influence training doctrine, procurement, and frontline tactics. It suggested updated instructions for pilots on managing throttle and supercharger settings across altitudes, emphasizing that the Mustang's efficient cruise allowed longer escort ranges but demanded conservative handling at high-speed dives to avoid compressibility effects. The report recommended logistic updates including stocking key spares, mirroring the radiator layout, and specifying spark plug types and torque settings for routine field repairs. It also proposed a set of tests for allied design teams to replicate performance figures and suggested a program of pilot instruction to harness the Mustang's strengths without courting avoidable risk. The institutional impact extended beyond immediate recommendations. Factories producing fighters reconsidered materials and assembly tolerances in areas flagged by Lurch as sensitive to performance, such as wing root fillets and control cable routing. Training squadrons revised curricula, exchanging some emphasis on aggressive short escort operations for practices emphasizing sustained cruising discipline and engine management. Intelligence units created a new protocol for triaging captured equipment and for coordinating rapid transfer of specimens to testing centers. Doctrine documents circulated at staff level began to use phrases that echoed Lurch's report, terms such as coefficient of drag and interval operational, to frame new operational planning. The epilogue traces consequences across 3 distinct temporal moments and closes our narrative on both human and institutional notes. 1 month after the tests, the mood in the hangar was pragmatic. The Mustang sat in a hangar bay stripped to a structural skeleton with annotated panels and with stickers marking components for replication. Sub-teams led by Carl Schmidt and Gerhard Klein had cataloged spare parts and produced a preliminary field maintenance guide. Dr. Weiss had produced a short technical brief that was circulated to procurement, which prioritized cooling system parts and certain fasteners. Lurch continued to log informal notes about handling and had begun to annotate pilot training manuals with cautions about high-speed dives. The immediate human outcomes were modest but meaningful. Fraser's unit had recorded his forced landing, and his crew received a formal citation for preserving the aircraft condition during egress. The sense at month 1 was that raw data had been captured and that it would now feed policy. 3 months later, the ripples became structural. Training squadrons had run simulation series incorporating the Mustang's endurance envelopes. New supply lists reflected recommended spare parts, and a small manufacturing adjustment committee convened to analyze whether certain tolerances could be tightened without significant production slowdown. In intelligence circles, the capture formed a case study in rapid exploitation, and a protocol was hardened for minimizing leaks while maximizing internal distribution.
Lurch's formal report had been partially summarized and distributed to design bureaus, who were now examining wing root treatments and control harmonization as potential areas for improvement or countermeasure. Discussion at staff level considered changes in escort doctrine, with operations adjusting rendezvous points and rebalancing fighter allocations across long-range bombing runs. 6 months on, the capture had accomplished durable change. Production specifications for new fighters reflected lessons learned inspired by the Mustang's combination of range and performance, with small adjustments to cooling and to control cable routing adopted by some factories. Training doctrine had shifted in doctrine manuals, and pilots in several units reported improved mission endurance and fewer forced retreats due to fuel constraints. Lurch's diary had been published after approvals in a limited internal edition, serving as a teaching text. Fraser returned to duty and later to retirement, where he occasionally corresponded with engineers about the smell of oil and the feel of a throttle. Institutional memory had absorbed the episode as a template for how a single intact machine could move from field discovery to design influence. The human note lingered in the way both men had treated the plane, not as an enemy trophy, but as a problem to be understood and solved. The final reflection is simple. What began as a forced landing became a pivot point in how machines were evaluated and how doctrine adapted to measured advantage. The technical conclusion rested on data, not on bravado. The Mustang combined an efficient fuselage, a motor Merlin tuned for performance, and a cooling architecture that allowed sustained high performance. Power output producing a range and endurance profile that changed tactical thinking. The consequence, institutionalized changes in training, procurement, and production. The protagonists returned to their lives carrying lessons learned in oil and in paper. If this story surprised you, tell us in the comments and subscribe for further reconstructed inquiries into machines, documents, and the people whose precise observations sometimes change the course of conflict.